I'm Georgios, and today I will talk about maximum likelihood estimation of Riemannian metrics from Euclidean data. Why we need this kind of metrics? I'm assuming you have this data set here. If you are lucky, you can get a normal distribution that looks like that. Since I don't trust my luck, we want to be able to define some distributions that look like that. As you can see, this distribution here locally adapts to the data and has the properties of the normal distribution, and we call it LAN. Usually in machine learning, which is my field, we assume that the data, they have a nonlinear structure, which implies smooth behavior in the data. In these cases, the normal distribution, which is a monotonic function from the center, usually fails. But why that happens? The main problem is that the underlying distance measure that the normal distribution uses. Due to this strict, let's say, distance measure, which does not take into account the underlying structure of the data, the normal distribution fails to capture the actual geometry of the data. We will try to replace this distance measure, but to do that, we have first to change the geometry of the space. What we'll do is we'll define a local inner product, let's say, for every point in the space, this positive definite matrix, and we want this inner product to change smoothly along the space. That's a Riemannian metric, obviously, and transforms the feature space into a Riemannian manifold. The first question is how to construct this metric. For our research, let's say, we based on the diagonal metrics only for computational efficiency, and let's say I want to compute the metric for that point here. The first step is to define a kernel. With that kernel, we can give a weight to all the training points in our data set and compute the local diagonal covariance matrix based on that weights. Then, take the inverse of this local covariance matrix, we can get a metric tensor. This metric tensor, hopefully, captures the local structure of the data. Yep. And also is based on a parameter. Okay, the battery probably is off. And it's based on a parameter sigma, which controls the curvature of the manifold. So to say how fast this metric will change. The question is how to choose this parameter sigma, of course. And that's what I will answer later in the talk. Having this metric, we can start talking about the geodesics, which, as you know, there are length minimizing curves under the Riemannian metric. And these curves, they tend to be close to the data due to this metric we impose to the space. We solve this optimization problem using the Euler-Lagrange equations and get a system of ordinary differential equation, and we use numerical solvers to solve it for our cases. That distance measure takes into account the underlying geometry of the data, and this is what we will use in order to define our distribution, our model. Together with the geodesics, we get two operations. It's the logarithm map, which takes 2 points and return the tangent vector on a tangent space on one of the points. And the inverse map is the exponential map. Important here that the length of the geodesic is equal to the Euclidean norm of the tangent vector. So now we're ready to build the intuition behind the LAN model. At first, as the normal distribution, we have to fix the mean value. Then we can compute the distances to all the points. These are the log maps for our case. And then since the tangent space is a linear space, we can define a concentration matrix there, let's say. And we can evaluate the normal distribution density on the tangent space. And this density basically corresponds to the density of the points on the manifold. As you can see from this slide, the density function is very similar to the one of the classical normal distribution. The only difference is that now we have the Mahalanobis distance, so to say, on the manifold instead of the linear space. This is a maximum entropy distribution under the Riemannian metric, but we haven't finished yet because we have to estimate the normalization constant, which is something that we heard a lot these days. In order to do that, we have to compute the following integral. As everybody knows, it's quite difficult to do that. Basically, it's analytically intractable. So we can use the trick and we integrate on the tangent space instead. Here we can use a Monte Carlo approximation scheme, and we can approximate this integral quite efficiently. The trick is simple. We just form a normal distribution on the tangent space where we sample from in order to estimate the constant. This is all about how to basically represent the infinitesimal small volume element of the manifold, how we can interpret that value on the tangent space. That's the whole trick. Now, having the normalization constant, we can start talking about the maximum likelihood estimates of this parametric model. Unfortunately, this problem is not convex, and we don't have a closed form solution, so we will use gradient descent and block coordinate descent in particular to solve it. And having a closer look to the objective function here, we have the data fitting term plus a regularizer in some sense, which is the normalization constant, which is based on the Monte Carlo integration. That term here helps us to talk about maximum likelihood estimates, as I said before, and they provide better solutions with respect to the first set mean, because we penalize somehow the solutions if the mean is outside of the data support, because the metric there is large, so the solution is going to be penalized by high normalization constant in some sense. Also, having the normalization constant, we can start talking about the mixture of lands using an expectation maximization algorithm. It's quite straightforward how to do that. The first experiments we tried is to see if we can actually fit normal nonlinear distributions that are nonlinear. And from the results, we see that the land already with one component can approximate good the underlying nonlinear density of the data. Also, we tried based on standard criteria to see how many components each model needs, and we see that the land votes only for one component, while the Gaussian mixture model needs at least 4. We extended this task to a clustering task, where we see that the land basically recovers the underlying structure of the clusters much better than the linear model. Also, we tried a real-world experiment where we tried to get the EEG measurements from humans and try to cluster their sleep, basically 3 stages of their sleep, the REM, no-REM, and the wake phase. And we tried to recover basically the clusters. Here, the data, again, they have this smooth and nonlinear structure as we want. They form a manifold, so to say. And from the results, we see that the land actually can manage to have better cluster alignment than the Gaussian mixture model. What I haven't said yet is how to estimate this parameter sigma, which is important for our case because it controls the curvature of the manifold. Somebody can say, okay, this one-dimensional parameter, so why you cannot take the one which maximizes the data likelihood? Yes, it's true, but we have 2 problems if we change the sigma. The first problem is that if we change the sigma, basically we change the measure of our space, which means that consequently the likelihoods are not going to be comparable anymore because the normalization constants now, they will have different scales. This is one problem. The second problem is that if we have very small values of sigma, it will imply that the curvature is going to be super large, which means that we will have numerical instabilities in our solver, so the geodesics cannot be computed in some cases. At first place, we cannot use this technique to pick the sigma, but we try to solve these 2 problems. In order to solve the first problem, we suggest to renormalize the land under the Lebesgue measure. So we have to do 2 steps. At first, we have to train the land based on the Riemannian metric we used under the parameter sigma. And then, after we have found the parameters mean and this concentration matrix, using importance sampling, we can renormalize the land under the standard Euclidean measure. Again, the trick here is simple. We multiply and divide with a proposal distribution. In our case, it's going to be a Gaussian. But this is debatable. In general, it's difficult to pick a good proposal distribution for the importance sampling. But from some empirical experiments we tried, we see that we have a good estimation of the normalization constant quite fast. The second problem of the high curvature, basically, it means that we cannot have the geodesics. So if we cannot have the geodesic, we have to construct one in order to bound the likelihood, basically, for that point. Since we don't have the true geodesic, we have to bound it by constructing a log map. So we have to bound first the length, and we take for the length the straight line that connects the 2 points, and we use for the distance the underlying Riemannian distance of this straight line. And also we have to pick a direction of the log map, and we pick as a direction the one which has the minimum eigenvalue of this concentration matrix we have found. This is how we bound the likelihood. So at that stage, we have solved the first problem, and we made the likelihoods to be comparable under the standard Euclidean measure. And also, we penalize the curvature of the manifold if this is high, in order to be, let's say, all the geodesics computable. And now we can pick the sigma which maximizes data likelihood. From the results, we see that in all the cases, there are always an interval of sigma, usually in the middle here, that where the data likelihood achieves the maximum. And this is what we were expecting for. Also, when the sigma is small, meaning that the curvature is large, we see that we have penalized a lot of the solutions. That's we see this high variance in the data likelihood. And when the sigma becomes large, what happens basically is that we flatten out the manifold. It becomes closer to an Euclidean space, and so the data likelihood drops. So today I'll show you how we can change the geometry of the space basically by constructing a Riemannian metric from our data or learning the Riemannian metric from the data. And we provide a systematic way of estimating the maximum likelihood estimation of, of the parameters of this metric. Then, having this metric, we can start talking about the geodesics, which are length minimizing curves that tend to be close to the data. In order to do that, we have to solve a system of ordinary differential equations, as you know. And at the end, having the geodesics, we can start talking about the land model, which is a maximum entropy distribution under this Riemannian metric. We provide the method to estimate the normalization constant and also how to estimate the maximum likelihood parameters of this model. And that's it. Thank you very much for your patience.
Questions?
Maybe I didn't get it from the presentation. The question is there some consistency analysis? So I mean, does the metric which is calculated by the way you present it, does it converge to the true metric of the manifold?
Basically, here we construct the manifold, so to say. So it's debatable here what happens. I mean, we provide a metric, and we build a model above this metric. But you can provide other ways of computing this metric, for instance, right? This particular metric has the problem that it is based on a kernel regression, basically, which means that you have the problems that the kernel has, right? If you have high dimensions, for example, or what happens to infinity, for example. I wouldn't say that this is the best metric that you can have. I agree with you, and I haven't did any consistency analysis. But there's a first try, let's say, to move this nice geometrical stuff to the machine learning community, where you have to learn something from the data. And of course, it's difficult to do that because you have a lot of, if you are in high dimensions, for example, you have a data set, you have a lot of empty positions in this data manifold, right? So how is going to be the metric there? With our recent work, we try basically to learn the metric automatically for the data. But this is not like this. This is more a simple approach, let's say, in order to start defining these geometrical models in the machine learning community, so to say. I don't know if I answered the question, but yeah, I haven't done any consistency analysis, let's say.
Is there an assumption then that there is some manifold around which the data is spread? Is it random manifold or what? I just didn't understand.
Sorry, I don't hear you a bit.
So there is an assumption that there is some manifold around which the data is spread.
Yeah.
So you, at this point, you did not analyze the properties of this manifold and did not try to recover these properties. Yes?
I mean, if you think that the manifold locally is like an Euclidean space, right? So this metric that we learn somehow, or we construct, captures the local geometry of the data. So we can say that locally, the manifold is equal to the tangent space, right? Isomorphic. So that's more or less the property, let's say, that we change the geometry of the space. So we don't have the dimensionality reduction scheme here. You have the feature space, and you have a metric on your feature space that tells you how expensive it is to move, let's say, in the space, in some sense.
Thank you.
Okay.
Yes, thank you. It's very interesting because it is a problem we try to solve for constructing a statistical test on adapting the threshold. Do you compare with method based on statistical depths, which are used when you have this kind of statistic of data points?
To be honest, I'm not a statistician. As I said before, I'm in the machine learning community. So our model, we just tried, to build something new in this community without providing all the statistical analysis at that stage. I hope in the future we have more, say, compact analysis about how this metric behaves and how this model behaves in general. But currently, this is what I have right now. We compared only basically our distribution with the classical linear distribution. And later we try to see how good this can perform in machine learning algorithms like clustering, sample generation, and stuff like that. But we haven't done any statistical analysis based on the land yet.
Okay.
Hi, thank you for your talk. I don't really understand because, like, I think that under the metric that you're trying to build, the distribution is going to be uniform. So why do you try to estimate it by a Gaussian distribution on this new manifold and not just like saying that it's uniform on the metric that you build?
Basically, I don't know. I don't think it's a uniform distribution because let me go back where we have the density. Yeah. So if you see here, this can be seen as a function, right? Forget about densities and distributions. If you forget the normalization constant, this is a function. And as you go further from the mean value, let's say, or the center, the log map is going to be increasing. So basically, the density or the function will get lower values. Then if you normalize it, you can get the density, right? So to say, if you are close to the square here in the center or the rhomb, you can see that this function is going to take higher values.
Yes, but I mean your point cloud is going to have a uniform distribution with respect to the metric that you're building, right? Okay, maybe we can discuss that after, or maybe I'm mistaken. But
because I mean the distribution is based on the metric, but the metric basically provides you the log maps, which means that the metric constructs the manifold, and then you define this distribution on the manifold, which means that.
Yeah, but the manifold you're building, like on this manifold, if you look at where the points are, they should be uniformly distributed with respect to the measure of the manifold, no? Because this is.
I mean, the points that define the manifold, not the manifold, the point. So it's like every point. This is a non-parametric metric, obviously. So you need some points in order to define this metric. This metric does not exist. We construct the metric, or we learn the metric in some sense. So as far as I have understand here, usually in your methods you have a metric, and then you work using this metric. In our method, we have some data only. Then we have
yes, but okay, you have some data. From this data, you build a new Riemannian metric.
Yeah.
So now what I think of, but maybe I'm wrong, is that under this new Riemannian metric, your distribution has a uniform density.
Okay, maybe we can take we can discuss that afterwards.
So let's take one final question. Please go ahead. No, I don't have.
It's okay. We don't have any question.
Sorry. So what is the reference measure to this density? It's a density with respect to what? Which reference measure?
It's under the Riemannian measure. So
of the manifold, then?
Yeah.
Which, the metric that you have learned?
Yeah, basically it's the metric.
And so the Riemannian measure of the metric which you have learned is locally the square root of the determinant of the covariance matrix of the data.
Sorry?
Locally, your Riemannian metric is the covariance metric of the data locally.
Yeah, basically.
But that's just what he was saying, actually. It's
yeah. When we construct the metric, basically, this is the metric tensor, let's say, at that point. In order to see the volume element here, you get the square root of the determinant of this diagonal matrix in that case. So if you go, let's say here, right? Since you are outside of the data, you see that the metric tensor increases, which means that the volume will increase, right? So you have high curvature, let's say, or the measure is large
remains
there.
constant, so that the density remains constant, because you have less points and more volume, so the density remains constant, so it's uniform.
I wouldn't say it's uniform. I would say that that change because you have the measure from the distance, right? I mean, that point, if you go even further, the distance from the mean is gonna be lower, so the density will drop even more.
Okay, so I think that's a possibility for discussions afterwards. So this concludes the session, and let's thank Georgios and all the speakers again.